Okay, so we continue. So we just decided that we need a mathematical representation of the meaning of the words, which would depend on the context of the problem that we want to focus on. That was all the discussion I tried to make if I was successful. So how to do it? Let's remember one of the problems we have studied in week 2 or 3, I don't remember. We had only one code session. Sorry about the noise, guys. Do you remember in that problem, we were feeding the characters. We obtained a teenage slang. Remember that one? We were feeding the characters. And for each character, we have used a one-hot vector. One-hot vector means you see one, the rest is zeros. Remember that example. And do you remember that it was a one-hot vector for each different character? I'm glad if you do. If you don't, I'm reminding you. And in that example, we had 3 sentences or 4 sentences. We could add as much as we want. So it was like an implementation of this idea. And we were using a simple RNN, not a sophisticated architecture, the least sophisticated architecture it was, remember. We had a corpus, so-called corpus, 3 or 4 sentences. We have added another sentence with Ali, thanks to Ali. It is good to see you. That was the 4th sentence we added. Then we have mapped each character, and we just counted the different types of characters. There were 21 characters, for example. It created a mapping vector of length 21 because we had 21 different characters in that. For that corpus, we have created that 4 sentences. And those vectors were one-hot vectors. And actually, this is in NLP literature, I just found out that this is called the localist representation, in which you represent each of your input of your language with a one-hot vector. It could be a character, just like we did in our example, or you could map any word to a one-hot vector, a single word. For example, word motel mapped to that word, word hotel mapped to that word, to that one-hot vector. These are the examples, these are the slides that I've taken from CS 224 because this is a very nice example. Guys, you would expect that motel and hotel would have similar distances, right? In meaning, because if you're doing something like a Google search, or somebody searches for a conference motel or hotel, you would expect the guy to be searching for a motel as well, although he says hotel. So actually, in this representation, we have a big problem. The first problem is, we have multiple problems actually. The principal problem, we just didn't care, was the vocabulary, the number of words you have, will designate the feature size, which is terrible. I mean, because in English language, we have thousands of words, and you'll be using a 1,000-long feature vector as the inputs. That's one problem. But let's say this is not a problem. You have fantastic computers. You have limitless computational power. You never have that. So, good. What is the real problem then? The real problem is that related to that similarity. Because this vector, as you can see, is an orthogonal vector. You remember what an orthogonal vector is? Let me show you, your mathematics guys. You have, I mean, EE guys, you have taken linear systems. You know what an orthogonal is. Orthogonal means the inner product is 0 between 2 vectors. So, and the inner product is calculated as, let me get my pen. I love my pen. I'm misusing my pen. So, where is it? Sorry. So, if you take, I cannot see my, arkadaşlar. Göremiyorum. Mouse'un ucunu göremiyorum. Okay, mouse'un ucunu göremiyorum ya, boş ver herhalde. Okay, so I guess you remember it. When 2 vectors are orthogonal, their inner product becomes 0. If their inner product becomes 0, that means they are different axes on a multidimensional space. And actually, these guys are not only orthogonal. There's a big problem with them. They're also orthonormal, which means anybody's distance from the origin, what is origin? I'll get there, is unity. So I have a list of words. I represent them with these zeros and ones. and their distance from the origin is all one. What is origin in this case? Origin, for this example, is a hypothetical word which stands equal distance to all words. There's no such thing. That's why actually that similarity thing cannot be defined and doesn't work for this model. Maybe it was meaningful for a character-based model, because actually it is not. I mean, because when you're doing a sequential model, when you type a character for any language, the next character's possibility is different for different characters. So words have in a sequential manner similarity, characters have in a sequential manner similarity as well. So actually, this is not the best way to do it. If we had some sort of similarity between the words, which would relate their sequential position plus meaning, that would mean something to us. Well, actually, we don't want to just relate to their sequential meaning yet, because sequential order yet, because sequential order will be handled by the recurrent models, our models. We just want to create a vector representation for all words where similar meaning words have similar vector distance between each other. So that Motel and Hotel's dot products will be closer to a word which is meaningfully just different than these guys. How to do it? This is the main problem, guys. Why this is the main problem? Because actually, I'm trying to push you to somewhere where you do, wait for it, a handcrafted feature extraction for your words. We could have done this. We could have just fed Motel, Hotel, all being one-hot vectors to a recurrent model. And we could just expect that some results, just like we did in the live code session we've done previously. In that case, your recurrent model would be responsible for two things. First, understanding the similarities between words, handling that, plus handling the sequential structure of the words so that your words, when just come up together, would make a meaningful sentence. So your model, when you're using a vector like this, your model should be capable of two things. Understanding the similarity of meanings between words, plus understanding the language model. Okay, I mean, we said RNNs are magical, that they can just simulate life. Remember the things that we said in the first week? That's true, but as the problem definition becomes difficult for RNNs, remember that they were difficult to train. So if we could create a vector representation where similar meaning words had similar distance and just closer to each other, it's lower distance, a little distance, and different words had, I mean, longer distance between each other. If we could create a vector space like that, we would be handcrafting the feature extraction part for the RNN so that that RNN will only be responsible for the language modeling case, which would make the RNN's job simpler, guys. And actually, this was done before the age of RNNs. Before the age of RNNs, in statistical NLP, people worked on algorithms to represent words' meanings in a similarity vector. So given a corpus of text, the algorithm reads the text and provides a distance for different words. This was already done in statistical NLP, because in statistical NLP, they had to handcraft the steps of the problem. Statistical NLP used traditional machine learning methods, not deep learning. They were not magical. You had to design your problem, you had to design your features, etc. So that part of the problem was still in the literature. One day RNNs came, and these guys who have been working on NLP and just started to work on deep learning those years, like 7 years ago, 8 years ago, said, wow, okay, RNNs could do the job magically for us, just learning the language model for us. But maybe if we could provide the similarities to the model beforehand using an algorithm, so that we represent the words within the context similarity with a representation like that, maybe the RNNs would learn better. So actually, this was the first part that was carried from statistical NLP literature to the neural NLP literature, which is called the word-to-vec algorithm. Word-to-vec algorithm, which I'm going to show in the next slide, is about word vectors. Words in a natural language are represented by not one-hot vectors, vectors like these, which represent the word in a Cartesian space, multidimensional, where similar meaning words have similarity in terms of vectoral distance. And that distance is calculated according to the problem definition, thus related to the data and by the data. Okay? And these vectors are called word embeddings, guys. Congratulations, you've heard the word embeddings a lot. You didn't know what exactly they were, but that's the story of word embeddings. And word embeddings are actually very important. There are very nice examples. This slide I've taken also from CS224. They have the word space of this, I don't know, it's 9-dimensional, right? 9-dimensional space. So in 9-dimensional space, it's difficult to visualize. So in 9-dimensional space, you have some distances, which you calculate the Euclidean distance of a 9-dimensional space. But in order to visualize it, you project those distances to a 2D world, like this you see in the figure. I mean, this is a common practice which these mapping engineers do, because the 3D world is 3D. So you create a world map, which is 2D. You do that kind of stuff because you keep the distances or you change the distance. There are different types of mapping. So this is a mapping within that 9-dimensional distance space, 2 dimensions. As you can see, say, think, and expect has similar distances. Come and go are very similar. So be, become, being, being are similar, kind of. That's the space you obtain. That's the purpose of it. So before you do any of your recurrent neural network stuff, before we do that, to understand NLP, we have to do this step. Create the proper word embedding using the word space. Actually, in your codes, if you've worked on word embedding codes in PyTorch and stuff, you just do this automatically because there's a library for that which does the word-to-vec algorithm. So that's the word-to-vec algorithm. How to obtain this? I had a timing problem. I should have read that sentence, but how to obtain this? Then I should have said word-to-vec algorithm. I just missed it. Okay, so the algorithm is called word-to-vec. It's pretty much new, actually. I mean, it was in the last decade. Everything exciting about AI kind of happened in the last decade, anyways. So the idea is you have a large corpus body of text, your context. Every word in a fixed vocabulary is represented by a vector, the word embedding. So you go in the text, you just take into consideration of the positions of words in the text. How? Depends on your algorithm. There are different types and different approaches in word-to-vec algorithms. And you calculate a word representation, a word embedding, regarding the similarity of the word vectors. And you just relate them to the word probabilities being in some places in the word, in the sentences. So this is an optimization process, by the way. All these algorithms are optimization based. Just the first thing about word-to-vec. Word-to-vec is not a single algorithm. There are different approaches to obtain a word embedding from a corpus. And different approaches apparently works better in different types of problems. I say apparently because this is not something I work hands-on, but that's what the literature says. So there are some common trends in different types of problems. Some of them use some type of approach in word-to-vec, some of them use some other type of word-to-vec. So what is word-to-vec? Word-to-vec is a combination of models. So I strongly recommend this tutorial, guys. I've seen it because in order to understand what it was, I just had to read it. It's from the Medium. In the last part of the slides, I've got reading suggestions. Remember, this one is there. So you have a corpus and you have some text, which is a language. It is not a set of words, be careful, which are a set of sentences. So the sentences being together in a language actually designates their similarity. So that similarity is not only about the meaning, but their existence in sentences. So you always say, I am going to work, I am doing. That's why most probably in any word-to-wake implementation, I and am are quite similar to each other, because not only they have some a meaningful relationship, relationship based on meaning, they have some sequential relation as well. So word-to-wake is an algorithm that accepts text corpus as an input and outputs a vector representation each word, which also is called as the word embedding. Good. There are many approaches. I just realized it very recently, guys. But there are really two common approaches about being up, top to down, and bottom to up, actually. One of them is the skipgrams. One of them is the continuous bag of words. Bag of words is, as the name implies, you have set of things in a bag. You make a histogram representation of their frequency. Skipgram is about, it just makes a probabilistic representation of words being in some certain places in the sentences. Will I get into the details of these algorithms? Guys, no. The details of these algorithms will take a lot of time, a few weeks maybe. So this is beyond the scope of this course. I strongly recommend you just get into these algorithms, at least learn them superficially, some of them, so that you may select the right one if it is an important part of your research, okay? But not quite the main focus in our in this course. So what to do? Well, they're already being implemented in many libraries in PyTorch, TensorFlow. You have them. You just use them. You just pick a word-to-wake algorithm. You provide a corpus. It provides every word with a representation, word embeddings. So word embeddings is, getting a word embedding is like an off-the-shelf tool for many, many libraries now, guys. Okay, we know what word-to-wake is, but in this course, we don't know how it works. Good. Any questions? Good. We know that to make a better language model with deep learning, we should somehow create a clever word representation. So our word embedding should be quality. That's what we learned. So we could make discussions. The output of word-to-wake we used to represent the words are called word embeddings. The representations are strange. One thing describes another. I mean, in different representations, you have different results. And some different words may be similar to each other, although they have totally different meanings, because the algorithms takes into consideration different things. Some of them takes into consideration the positions more. Some of them, their frequency in the corpus more. For example, in continuous bag of words, since it's about the frequency, the words that are being used less in the corpus will have a less qualified representation, the literature says, which makes sense for a bag of words kind of representation. So what word-to-wake does is it vectorizes words in a mathematical representation, which provides a similarity vector for us, and which would be useful for your recurrent model. So for that matter, I've seen it in one of the blogs, guys. Word-to-wake is similar to an autoencoder. I realize we haven't discussed autoencoders in any of my course. That's my bad. I should have put them. Autoencoder is like a convolutional neural network which creates its features, higher representations, using only a given input data, no labeling. So it is like an unsupervised model. Word-to-wake is like a unit architecture where you put the images, for example, and you try to obtain the same image. So you say the network, so it's like a unit architecture. So it's like a hourglass architecture. The representations becomes, in resolution smaller, then it becomes larger. So in order to just recreate the same image from smaller representations, you have to understand the features inside the image. So an autoencoder creates features from a set of data. For that matter, word-to-wake is like a feature extractor. So that's similar to an autoencoder in images. Never forget this. The word-to-wake is a feature extraction is similar to a feature extraction step for a deep learning system. So actually, it's a clever step for that matter. Okay. But there are very nice implementations. I just checked the internet. They've implemented to anything. I mean, because the last decade had been crazy about any implementation. This is a very nice distance figure. They actually implemented the WordNet for C language, guys. And that's very nice. For example, the C out and end line are together. Free and delete are together. fprint and print are together. Calloc or realloc is together. If you're into C, just see what I see. So false and true are together, which makes totally sense. Which means that word-to-vec works very fine. And you definitely need that for a language model. This was the first step. So whatever code you're going to observe in your projects or in your graduate life or your career, professional career as well, I don't know, you will have to work on a word embedding problem and you will have to find the proper word embedding. Good. So before I finish, I'm going to make a brief and gentle introduction to one of the fundamental architectures, which we are going to cover the next week, which with more important architectures and concepts. Any questions about word embeddings and word-to-vec? Sorry. I guess not. Okay, so before we finish, I'm going to introduce you the encoder-decoder architectures because in NLP they are commonly found and they are something like a unit of NLP. We previously talked about RNNs being able to handle the NLP problem, but we did not talk about any architectural designs, and actually encoder-decoders are the fundamental sequence-to-sequence, many-to-many input-output models used in many applications, guys. So let's see what they are. You have an encoder, which is an RNN model on its own. You have sometimes an in-between model, and you have a decoder. So it is like this guy processes the input, and using a self state or a hidden state, carries the input to a higher representation, where if we have this part, optional part, which processes that part, changes that part, so that that meaning is transformed properly to the second part, which would provide us the output. So if this Turkish to English translation, the first part understands the Turkish words and meaning, the middle part will get the meaning, language-free meaning, just process it so that it is suitable to be fed to an English word in terms of the order of the concepts in a sentence. And this guy creates the new language. And this red guy, since the output is English, is capable of, and just, I mean, it's capable of the organization of words in English language, the grammar and syntax, whatever. That's a common architecture used in sequence-to-sequence models. Because well, instead of this, you can use a single model. Just put an RNN there with many hidden models. Why not do it? Because this is more transferable, just like Ali asked. And this is easier to train because it is easier to debug. You could change the problem. For example, you could only train the encoder for some words with Turkish, then add this part, then add the other part. So you could train it step by step. So that's been widely used in the literature. So encoder-decoder model consists of 3 parts. Encoder, intermediate encoder vector, which is a model and optional. It is only a vector sometimes, so there's a model there. And the decoder. So encoder is a stack of recurrent units. STMG is single one, multiple ones. It collects the information of the input. Its purpose is to process the input and transform it to a higher representation. So if it is Turkish to language translation, just like I said, its purpose would be to carry the Turkish input to a language-free representation of meanings. In a question answering problem, it's both input and output being English, its purpose would have been to understand the concepts and create that conceptual word in the encoder vector. Okay. So the second part, the encoder vector, well, this is a model or just a vector. It's optional, I mean, depending on your architecture. It is the output of the first part. So in that part, you have, you have a higher level representation. It is difficult to tell what it is because these models are not transparent. So you use that representation to be fed to the final model, which is the decoder model. And in the decoder, this is still a stack of some recurrent models, which is, you may have multiple recurrent models, whatever you want to have. And this is where that higher representation is being converted to a varying length output, whatever your problem is. Okay? And this is a very common approach used in NLP-based problems. It could be a question answering, or it could be a visual question answering. There are visual question answering problems. One of my students started working on that. So you have a picture, you have a question, and you need an answer. So you have a picture with some guy with a baby, and you have a question: what is the color of the baby? And you have an answer. For that model, you would need an additional visual decoder, which would be fed to the higher representation, and the higher representation be fed to the decoder kind. So any NLP-based problem is being handled by encoder-decoder architectures. And if you start working on this literature and just making a survey about it, you will come across these architectures a lot. Any questions about encoder-decoder architectures?
I have a question.
Please.
First we have the encoder and the decoder, but how do we know when to decode the vector? Do we need maybe a dot at the end of the sentence?
Well, that's a good question, but that depends on the application, right? Because maybe it is not a dot, maybe it is not a English word, but yes, if you could model your problem, it's a question. We're talking about question answering problem, right? You're asking that for that one, for example. Let's say it is not a dot, it's a question mark. Well, if you feed it that way, if in your training data, all the words finish with a question mark, the model would learn that when the question mark comes, that's the end of the representation. It would learn that, regardless of the length of the sequence. So doesn't it make sense?
Okay.
I mean, you're asking how does it learn? It learns because all the text, all the corpus included question marks in the data training set. That's how. So most probably, if you trained with all question marks and you provided a question without a question mark, maybe it won't answer because that's what it's training. Because you see, as you feed, the encoder vector will be shaped. And as you fed the question mark, encoder vector would be ready to be passed to the other side, right? So it makes sense.
Okay.
Okay. Okay, any other questions?